We will move to the next presentation, which will be given by Professor Vasilije Manovic from Cranfield University, and the topic will be focused on solid-based adsorbents. The first presentation is from Professor Mason Wang is liquid-based. Now we have focused on solid-based. So Professor Manovic, thanks. And yeah, I can see your slide.
Yeah, thank you. I'm just trying to set up everything that it works. So
excellent. You can start. Yeah.
Good. Thank you. So thank you again to Menhoi for good presentation, interesting with a lot of data, and also for that part talking a bit about in general about carbon capture and storage. I also wanted to say something like to give a brief introduction about carbon capture and storage, but I didn't want to be repeating too much what you already heard, and I just was rearranging a bit my slides now during previous presentation. So just first to introduce myself. I'm Vasilije Manovic, and I'm professor with Cranfield University since 2013. Before that, I worked for 8 years in Canada for Kenmet Energy, which is their government research institute, which belongs formally to their Ministry of Natural Resources. And before that, I was working in Serbia, where I was born and got my PhD, and left in 2005 as lecturer or assistant professor. My research was mainly related to energy technologies. I started in energy and environment. So I started with looking for technologies to desulfurize coal combustion processes like coal-fired power plants, and I started working on carbon capture and storage about 20 years ago. And the main technology that I have been working, I work in different CCS technologies, but the main technology that I have been working is calcium looping, which is using lime, calcium oxide, as solid-based sorbent. Okay. So, as I said at the beginning, I would like just to say something about carbon capture and storage. We recently, not recently, but for all time since I have been working on carbon capture and storage, we heard many times that whether is that necessary, whether we need carbon capture and storage, whether we need at all fossil fuels to produce carbon dioxide and then to clean that, to remove that carbon dioxide. Why we don't go simply with renewables? And those are now, although my background is chemistry, now I'm more thinking about such things because after so much work by many of us, working on different carbon capture and storage technologies, there are still such questions. So I usually want to say something that people understand why we need at all carbon capture and storage technology and why that's essential. First of all, in carbon capture and storage processes, we have three main steps. We are separating CO2 from gases containing from gas mixtures containing that greenhouse gas, and we normally consider large point sources of CO2. Once we separate CO2 from other gases, which is necessary step, sometimes I can hear a question why we just simply don't store everything underground, why we don't just take flue gas and store underground, just to let you know that it would not be economically feasible. It would be very energy intensive because usually flue gas contain say 5 to 15% of CO2. So order of magnitude larger volumes of gas would need to be transported and processed if we don't separate CO2, if we don't capture CO2. Then next step is transporting CO2, and when I started working on CO2 capture, transportation and storage, we at that time even considering other options for CO2 storage, such as storing that at the bottom of oceans. But yeah, there are some legislation-related issues that were not encouraging to proceed with such approach, because in some cases, in some countries, according to their legislation, CO2 is considered as waste, and storing waste in oceans is not legally allowed. So now we are mainly considering depleted geological formations. We are considering suitable geological formations for storing CO2, and they are often depleted oil and gas reservoirs. And now, as Mei Hong mentioned, yeah, we can use CO2 for enhanced oil recovery, which means when we have depleted oil and gas reservoir, to increase oil production, we can inject CO2. There, my feelings about that are divided, and you often can hear that it basically doesn't help us to reduce concentrations of CO2 emissions and concentrations of CO2 in atmosphere, because in that way we are increasing production of fossil fuels. So what are main challenges? We still haven't deployed the main. We are still not where we wanted to be with carbon capture and technologies. And just I wanted to classify those challenges. First of all, technical challenges. I can be talking about that, and I suppose most of us are here engineers and understand technical issues and how they can be solved, etc. And we have many carbon capture technologies which can work commercially if we look at technical points of view. And even we heard about amine scrubbing, which was commercialized technology even before we were thinking about carbon capture and storage, because, for example, in petrochemical industry, they used amine scrubbing to separate CO2. So from technical point of view, it's not barrier, and we have solutions. The next thing, when we talk about carbon and capture technologies, I usually consider the next challenge are economic and commercial challenges. First thing that I always mention is not doing CCS is more expensive than doing. Yeah, we need money to do CCS, but not doing CCS is expensive. First, we need to reduce greenhouse gas emissions like CO2. That's without doubt. And we have different approaches, including renewables, nuclear energy efficiency, etc. But if we try to go only if we exclude any of solutions, if we any of approaches, like even if we exclude CCS, everything else becomes more expensive, and we are not achieving CO2 emission reductions. I will come later to that point during this presentation. So one thing is the next challenge is I try to classify them to be what I realize here is more and more challenging. For example, when we are going from technical challenges, economic challenges a bit more important. Lack of policies and regulations is also even more important, because it's still we still have no clear policies and regulations in many countries whether we would like, how to decarbonize economies and what's the role of CCS in that case. And finally, I think social psychological factors, such as like public acceptance, or even I consider that as myths, that CCS is expensive, or that we have no technical solutions for CCS. Those are only myths, or even something which is used with, by those who are proposing some competing strategies. Instead CCS, we can do something else. And CCS, you will often hear CCS is competing with renewables. It's fact, yeah, there is competition. There is competition for resources. There is competition for funding, but the goal is same. CCS and renewables. We need both of them to achieve sustainable decarbonization of economy. I will come to this point also a bit later. So why we need CCF? I just show this example, and I intentionally use something which was published 10 years ago. Nothing changed even now. For example, when you look what was in 2013, what were predictions, similar predictions are now. So the fact is that global electricity demand is growing. Renewables or nuclear can only partially solve issues related to increased carbon dioxide emissions. Surprisingly, even if we talk about that we would like to, phase off, or even I can hear now some calls to ban fossil fuels totally, which, would be simply impossible, to run economy by banning, say, fossil fuels. So regardless to all of that, the reality is that we still haven't reached the peak of production of fossil fuels. Although we are talking, about reducing their extraction use, etc. In the future, it's expected to use even more natural gas, which is using natural gas also contributes to CO2 emissions if it's used for electricity generation. And what situation is now? We basically, because increased penetration of renewables in energy grids, we have two solutions to balance grids. We simply cannot, for example, wait for wind or sun and that we run economy when there is wind and sun. So we need something to balance. And yeah, one possibility is energy storage. We still have no energy storage capacities at scale. First thing that when we say energy storage, and especially if we talk about electrical energy, first thing that is in our mind are batteries. How it would be sustainable, for example, to proceed only with batteries for energy storage? Give you just example. If you would like energy storage, its capacities at the scale needed for UK only, we would need to import all lithium around whole world, all lithium produced, just to have enough batteries to store electricity in the UK. So at the bottom of this slide, what I wanted to conclude, for a long time we have been talking only about renewables and that we can solve all problems in that way, but it may be even a surprise for somebody. Although these days we are talking, for a long time we are talking that we are reducing carbon dioxide emissions, and that's narrative usually that you can hear. But no, we are not reducing. If you look at the data, we are increasing CO2 emissions. So we still, only with renewables, were not able to achieve significant CO2 emissions. So I think for sustainable decarbonization, we will need in the future mix, and especially including both renewables and CCS, which will allow sustainable transition to zero carbon economy. Again, this slide is what we believed 10 years ago, and what CCS technologies we were considering, and even at that time, amine scrubbing, solvent-based scrubbing, that was already commercialized technology. Technology that I will talk today is solid sorbents-based CO2 capture. So for that technology, we believed, that needed to be carbonized 7-8 years ago at least, not to be commercialized at least 7-8 years ago. And you will see later we are going towards commercialization of such technologies, solid sorbent-based technologies, but still we are not at the scale what we wanted. And of course, there are some other technologies, and in general, I think with CCS that we are behind the schedule, what we forecasted and what we wanted. So you already saw this slide, so I will not be talking much, but just wanted to put calcium looping technology that I will be talking about in the context of this slide, how we consider carbon capture and storage. So we have post-combustion. So we have power plant, we generate heat, we use that heat for steam cycle, we generate electricity, etc. So in the case of post-combustion scenario, we do business as is, and after that we have a CO2 separation. This is the retrofitting scenario, and it could be whatever we want. In this scenario, we can have amine scrubbing, but can also have calcium looping, which is, just to mention again, calcium looping is second generation of the carbon capture technologies, and we wanted to develop second generation carbon capture technologies with aim of reducing costs, but also to diversify carbon capture and technologies, because not only one technology would be the best in all case scenarios, in all applications. So that's about post-combustion. Business as is, and we retrofit capture plant that could be also calcium looping based capture plant. The next scenario is pre-combustion scenario. So we have carbon-containing fuel by different chemical and thermochemical processes. We are converting that fuel and producing usually gas containing carbon dioxide and hydrogen, which is carbon-free gas, and we are using directly hydrogen in processes to generate heat and power. So, and as product of using hydrogen, we are no product of that reaction of burning hydrogen or using in another process is not carbon dioxide. Carbon dioxide is already separated and ready for compression, conditioning compression, and transporting that and storing. Finally, we have oxy-fuel combustion, and I will not talk much about that now, because we'll mention later, because a component of calcium looping is oxy-fuel combustion. But just to say, in general, in this technology, we separate first air to have pure oxygen, and if we use pure oxygen in combustion process, we produce high purity CO2. So we don't need any capture process after combustion process. So when we talk about solid sorbents for CO2 capture, many of them have been considered and developed. Probably you can find thousands and thousands of papers of different natural sorbents, but also synthetic sorbents. And my aim will not be now here to be talking about many different options that I said you can find in thousands of papers published by many researchers. I would like just now to say that one of important property of materials that we use for carbon capture is their cost, and that they are available, that they are abundant, and they are environmentally friendly. Just that we are not using materials to capture CO2, and then we cause other environmental damages. So calcium looping in calcium looping technology, we are using limestone as a natural sorbent, and 10% of sediment rocks are limestone. We can use also in those processes dolomite or magnesite, but the limestone is simply the most tested and the cheapest sorbent for CO2 capture in these processes. Processes that we will be now talking about are efficient. They can separate 95% plus of CO2, and their main advantages are low energy penalties for carbon capture. So we will see later how. And as I said, why we are at all developing, when we already have commercialized carbon capture technologies, why we are developing second generation technologies such as calcium looping, because we are looking how to reduce costs. Solid sorbents, we have really many of them that can be used at low temperatures, high temperatures, and the calcium looping is a process where we use carbon capture is happening at a high temperature at 650, which is one of the advantages of the process, and again we'll talk about that in a bit more detail. So the process is relatively simple. It's based on a reversible chemical reaction of decomposition of calcium carbonate, producing calcium oxide, lime, and CO2. So how we run that process? This is a phase diagram of the system of containing calcium oxide, carbon dioxide, and calcium carbonate. With increasing the temperature, with increase the temperature, calcination reaction will be happening. With reducing temperature, we can run reverse reaction, which we call carbonation. So usually in this process, depending again what's CO2 concentration in a gas that we are processing, but for example, if CO2 concentration is 10%, we can go in carbonation. That means reaction to capture CO2 can go up to 700 centigrades. When considering calcination, we want a gas containing that's here, say 95% approximately CO2, and if you look, the minimum temperature must be somewhere here, which is 850, but yes, from thermodynamic point of view, but from the point of view of kinetic of chemical reactions and the intensity of the process, we usually go up to 900 centigrades. We run sorbent regeneration reaction, which we call calcination. So the process is schematically presented here. And as you can see, we have two main reactors, which is carbonator and calciner. In carbonator, we operate carbonator at 650 centigrades. In that reactor, we have a calcium oxide reacting with CO2, and the saturated sorbent is basically we say partially carbonated calcium oxide, because this reaction never happened. We will see also it's never going to happen 100%. 100% conversion. So that's one reactor. We circulate material from carbonator to another reactor, which we operate at, as we said, 900 centigrades. And in that reactor, we have decomposition of calcium, partially carbonated calcium oxide. We decompose calcium carbonate and produce CO2. CO2 now. We need to heat this reactor. You see, we need 900 centigrades, and now we cannot afford to heat this reactor like by what we do usually in power plant by air. We need pure oxygen. Although we need pure oxygen, because if we have here air and fuel, when we say coal, it could be any fuel, could be natural gas, whatever we want as fuel. So we need pure oxygen in order that we don't dilute CO2 by feeding this reactor with air, because in that case we would produce here again mixture of CO2 and nitrogen. We don't want that. We want, say, 95% plus of CO2 produced. To have oxygen in this process, we are usually running air separation unit, which is usually commercially available cryogenic oxygen separation. And so from this process, as you can see, we have from a gas containing flue gas containing CO2, diluted CO2, we have at the end as outlet, the outlet of the process, concentrated CO2, ready for compression and transportation and storage. Few things to pay attention here are, okay, you would consider this is energy-intensive process, because we need to run this reactor at 900 centigrades. We are using fuel, etc. That's correct. But on another side, this reaction is endothermic. We need energy here, heat. But in carbonator, capture reactor, we have exothermic process, which is happening at 650. Exothermic process at 650 means that we generate heat at 650 centigrades. It's a very valuable heat. It's high-grade heat. So we are not wasting this heat. We are using, depending on industry where we would like to deploy this process. But for example, if we talk about power generation, we just simply integrate this heat in the process. We generate additional steam, and we increase power output of existing power plant. So what's now the difference? Many carbon capture technologies, if not almost all of them, they are reducing power output if we of existing power plant. Calcium looping is unique from that point of view because we generate additional power output. So that's one thing unique about this technology. Also, you can pay attention, spend sorbent to cement industry. In this process, since the material is during cycles losing activity, we always must make up a bit. It's usually say 5%. During each cycle, how much we have in the system, we add 5% of fresh limestone. By adding fresh limestone, of course, we must be taking something from the system, the same amount, because mass balance. And that's material that we call spent. It's basically material of a lower activity taken from the system. But that material is excellent feedstock. We don't need to dispose that, and it's not waste. And we can use that in cement industry, in iron and steel industry, and in some other industries where they need lime as feedstock. So about this technology, just to mention, that's another another unique that we can make synergy. Few synergies with other processes, as I said, such as the cement industry, iron and steel industry, because we are using the same process to decarbonize existing gases from those industries containing CO2, but waste from calcium looping process we use as feedstock in that industry. So basically, in those scenarios, we even have no cost for sorbent because we just use that anyway in those processes. So how this is just a simple schematic representation of the process. Usually we have two fluid bed reactors, as we said, carbonator, and feeding flue gas, or can be, we often usually talk about flue gas, but it can be any gas containing carbon dioxide. It reacts with calcium oxide, with solid particles of solid material, particles of calcium oxide, and during that reaction, calcium carbonate is produced. In these transfer pipes, material is transferred to calciner, and in calciner as I said, we need heat to increase the temperature, order of magnitude 910 degrees, and CO2 is produced, and material is circulated back again solid material is circulated back to carbonator. That's just a simple, simple schematic representation of the process that you see how it basically works. So, what are the main challenges for? First, I will mention some benefits. Already mentioned them. Inexpensive sorbent, usually it's considered to be $10 pounds or something like that per ton. So very, very inexpensive material to be used for carbon capture. The main components needed to design calcium looping system are already commercially available. When I say the main components are fluid bed reactor systems. Another advantage is low projected cost for CO2 capture. And I see here, even now, during previous presentation, I said in some applications, 20 ton per CO2 avoided. So there have been already discussion during the previous presentation how we are accurate about these costs. And I wanted here to mention, we have done probabilistic analysis of economic studies, if I can say in that way, of techno-economic studies of calcium looping. So yes, we are very accurate with process simulations. That's order of magnitude few percentages, but economic assumptions are critical. So we compared in one paper, I didn't have time just to find it now, but you can take a look. I think it's published in Applied Energy in 2017. They compared estimated levelized costs of CO2 avoided for calcium looping from different papers and looked at their assumptions. In different papers, you can see with some assumptions that cost of CO2 avoided by this technology can be 10 to 15, if I remember, dollars. But some researchers doing techno-economic analysis for the same technology applied for power generation, applied it to decarbonize power generation, calculated, I think, $120 per ton. So you see with economic assumptions how wide we can go. The most realistic scenarios, if we talk about power generation for calcium looping, even considering probabilistic analysis is somewhere at the order of $50, 50 pounds, euros, or something like 60 per ton of CO2. Again, it heavily depends where you deploy these processes. One country, how much is labor there? How much is limestone there? How much is coal there? Many different assumptions. And yeah, you can, if you take all pessimistic assumptions, you can go up to 120. If you are optimistic about everything, you can go to $20 per ton of CO2 avoided. Yes, and I mentioned that CO2, that limestone is basically environmental embedding material because it's 10% of all our sediments already. And one of significant advantages of technology is the opportunity to increase power output if we need additional power output, and we really usually need, because carbon capture and storage technologies are often criticized that regardless to increase demand for power, if we implement carbon capture and storage, we decrease power output from existing power plants. So this is a good selling point about calcium looping technology. But the most important are challenges. So we have some, challenges related to material that I have been doing a lot, maybe until 10 years ago or before that. So those are related to that decay of activity. And another problem is that calcium oxide is also reacting with sulfur dioxide, and due to that, activity of calcium oxide is reduced. But it's at the same time bad news, but also good news, because we are cleaning at the same time flue gas, removing sulfur dioxide. If we have calcium looping, we don't need additional plant for desulfurization. Since we operate calcium looping in fluid bed reactors, it's normally in such reactors we have attrition and elutriation, which means that we are losing some material from the system. We need pure oxygen, and that's a relatively expensive process to produce cryogenic separation of air is relatively expensive. We had some other solutions, but still we predominantly are considering cryogenic separation of air to produce pure oxygen needed for calcium looping. Produced CO2 stream is corrosive in the case of calcium looping because we have oxy-fuel combustion in calciner, and we always have a surplus of oxygen. And we have using fossil fuels, so there is some steam, there is some oxygen, there are some acid gases, and definitely yeah, that's corrosive. And this technology is also considered capital intensive, but because you coupled fluids and bed reactors, it's not cheap to construct. But we will see again later, it's not necessarily always capital intensive process. In some cases, we already in the system have some reactors that we can use, not necessarily always to build new reactors. In this case, just is presented simply how sorbent is losing activity. So if it was at the beginning calcium carbonate, you calcine that. This means no CO2 in material. During next cycle, it's usually going about 70% conversion. And, with the number of cycles going down, usually, we consider some final activity. If you expose material to say even 1,000 cycles, there have been publications, when researchers were testing material for 1,000 cycles, and usually, at the end activity is 7-8%. So you cannot use material which is only 7-8% active. And the solution was to make up always fresh material and to purge portion of material from the process. But it's increasing the cost of the process, especially in the scenarios where we have no market to use that spent sorbent that we purge from the system. For example, in the case of power generation, we usually don't have that opportunity to use for something spent sorbent, and we need to think about other solutions. We were thinking about other solutions, how to reactivate that material. And usually we consider that sintering is happening in the material, which means decreasing pore surface area, decreasing pore volume of solid particles, and that's a reason for lower activity with each cycle. So another interesting thing about solid-based sorbent, specifically if we are talking about calcium oxide, is that we have when we look at kinetics of the reaction, we have 2 stages. At the beginning, if we expose calcium oxide at high temperature to CO2, it reacts very quickly in the first few minutes. But after that, there is almost no reaction or very slow reaction. So at the beginning, we have a reaction rate controlled reaction, and when we are designing processes, we are only considering this because process would not be practical to wait for days or for hours to capture a few more percentages of CO2. So, and that stage is slow and diffusion controlled. So what's basically happening? Just imagine a surface of calcium oxide. Doesn't matter how it looks like, porous or just a flat surface of calcium oxide. At that surface, okay, when you start reaction, you have direct access of molecules of CO2 to calcium oxide. Therefore, quick reaction at beginning. But you see this around, this is a layer of calcium carbonate. Now, at the surface of your reactant, you have product layer. and now your molecules of your gas would need to get in touch with calcium oxide. And okay, now we have different theory how it's happening, whether we have whether we have gas diffusion of molecules of CO2 to react with calcium oxide, or we have a kind of solid state diffusion of ions of calcium oxide diffusing towards the surface, to this interface of solid and gas, and the reaction is happening here. So it's from practical point and engineering point of view less important, but just that you understand a bit that I explain a bit fundamental science behind this fast and slow reaction rates. So that's about sintering and loss of activity. Another problem, which I said is at the same time problem, but also good news, is sulfation, because calcium oxide is reacting with sulfur dioxide, and this is just couple examples of TGA tests when you have sulfur dioxide. This dashed line is showing how much of sulfur dioxide during cycles is formed in the particles. You see, during each, this is CO2 capture, then regeneration, capture, regeneration, but if you in flow gas have CO2, you always have less and less calcium oxide available. So yeah, from the point of view of CO2 capture, using this sorbent, it's not good thing to have sulfur dioxide. But if you already have sulfur dioxide, it's good news that in the system you have calcium oxide to remove that sulfur dioxide from the system. This means only that we would need a bit higher makeup ratio of fresh sorbent. Another possibility to recover material, to increase activity after it's spent, is hydration. Just to give you some ideas what we have been doing, how we were trying to improve material performance in calcium looping system. So I think that material was, after maybe 30 cycles, and conversion already, even you see after half hour, conversion was only 30%. In the first cycle, when you start using material, it's usually at least around, say, 60-70%. So this material is not much contributing to CO2 capture. So one of the best techniques to reactivate that material was to expose that to steam. So the same samples, when we exposed to the steam, you see it performed same, even if not better, than fresh material. So that was one of the main reactivation techniques that we considered. But the main problem, when you reactivate calcium oxide with steam, you will get fragile particles, fluffy material that you cannot handle in fluid bed. It would be evaporated. So we needed something more to do, not only to hydrate and reactivate by hydration. One of idea was using pellets, and that was one of the first tests, even when we just tried whether it will work at all, and we were doing that by fingers, so you see some pellet particles. But when we found that it worked, that in that case we improved mechanical strength of particles, we improved activity by hydration, and we had commercially available and inexpensive binders that we also can add to improve mechanical stability, such as calcium aluminate cements. We started producing this material in a kind of pelletizer, mechanical pelletizer, and how it looks like you can see, in this photo and in this schematic representation of the process. So we have this vessel, we add material which we would like to reactivate and to pelletize. We have blades, one at the bottom and one on the wall, or on the side wall. So these blades we can control speed of rotation. We can control how much we are adding water, and by those parameters we were able to, for example, even to control the particle size of material that we were producing. Particle size of pellets is important if you have fluid bed systems. So at that stage, at that stage of development of materials, we were thinking, okay, now we enhanced activity. Many good things that I mentioned already, but we said, okay, we were thinking, why not, now since we are making new material from powder, we can add even something else in that material. And we considered catalysts or even oxygen carriers. I will not be now talking much about catalyst, but in the case, what's the story about catalyst in the processes? If you have process that you need something to capture CO2, sorbent for CO2, but also you need a catalyst in the system, you can put them together in the particle. And to have a composite particle with sorbent and catalyst. But more interesting was that to adding oxygen carriers. Okay, oxygen carriers. What was the point of oxygen carriers? If we have, when we want, okay, this is a particle which is partially carbonated, CO2 is captured, and we need to regenerate. If we have metal oxide, which would be reacting with fuel, which is usually methane, natural gas. And during that reaction, fuel reacting with metal oxide, heat generate, we can in that way regenerate sorbent. So that was interesting what we were doing. And when we're considering what oxygen carrier to mix with sorbent, these are some criteria that we were considering, like we didn't want really that our oxygen carrier is toxic because handling that in fluids at bed and due to elutriation, causing environmental health and safety issues or whatever. We needed to consider, among other factors, oxygen transport capacity, because more oxygen and more exothermic reaction would mean that less of oxygen carrier you are adding, mixing with sorbent. So just briefly to that you see what's idea of the process that we wanted to design. So we wanted in that way to avoid expensive air separation process. So we had, in this case, okay, you can recognize already these two reactors, carbonator and calciner. And we needed air reactor. In air reactor, composite material is oxidized. Composite material is transferred from air reactor to calciner, and we feed calciner with methane. You remember, instead we needed, in previous case scenario, methane and oxygen, separated oxygen. So we need now only methane because we have oxygen in oxygen carrier. We in that way generate heat, and then material is transferred. These dashed and solid arrows are different scenarios that we considered. But okay, we could transfer the material to carbonator where CO2 capture is happening. CO2 capture from flue gas. That's business as is. Excuse me. What we still were able to do with solid sorbents, during the pelletization process, we were able, when we were making composites, we were able to produce core containing, say, one kind of material, which usually we wanted in this core to have material which is more expensive, to don't be losing that from the system, or if we could not avoid something which is toxic, like toxic catalyst, to put in core and to have a kind of shell. So we developed technique to produce core in shell sorbents, materials for CO2 capture, and composite materials containing also catalysts or even oxygen carriers. This is just scanning electron microscope image of shell. So inside was, inside of this shell was a core, and just to demonstrate that it really worked, that we were able to produce core in shell pattern. That material also was we were doing tests in fluid-bed system to make sure that they are resistant to attrition, we achieved that by adding calcium aluminate cement. As I said, I will not be now also, as I haven't talked about all material, it would not be feasible to talk about all materials. I will not be mentioning many technologies for many projects where we already have a demonstration of a calcium looping process. But one of the first demonstration at beginning, we were developing this process for power generation, to decarbonize power generation, and in one of largest project 10 years ago was 1.7 megawatt calcium looping capture plant, which was used to decarbonize real flue gas from 300 megawatt coal-fired power plant, and that was demonstrated. And as I said already, there are many, we needed simply to look for more opportunities for this technology, because power can be produced in many different ways, but we have technologies that cannot be easily decarbonized, and they are carbon intensive. And one of recent projects is clinker, which is how we decarbonize, how we can, by calcium looping, decarbonize cement industry. So you can already recognize those two reactors, carbonator and calciner, and the spent material is used as feedstock in a rotary kiln. So we don't need to be adding fresh limestone to rotary kiln. We are just using line from a calcium looping cycle. And when we heat integrate, because these two reactors, they operate at high temperature. Rotary kiln also operate at high temperature, more than 1000. You have a huge savings when, because your material your lime is already preheated. You don't need any heat to calcine your lime in a rotary kiln. These are just examples how we were changing our focus from power generation to industrial decarbonization using calcium looping. About those large projects, I wanted to mention our current project at Cranfield University, which is a HYPER project, which deploys. Previously, we talked about calcium looping for pre-combustion, and even from at the beginning, from my slide, you saw that we have three scenarios for carbon capture, and that was calcium looping in a pre-combustion CO2 capture scenario. But now we call usually that absorption enhanced steam methane reforming for blue hydrogen production, because now it's attractive, to have processes to produce hydrogen that can be used to decarbonize many different processes, technologies, etc. Basically, the summary reaction, what's happening in this process, which we are now building and should be commissioned at beginning of next year and tested during next year, is that we use natural gas with water, and it in reaction with this solid sorbent, calcium oxide, is producing hydrogen and This is calcium carbonate that's going to be regenerated in calciner. So the process is basically the same, but just from a different gas mixture. In this case, we are taking CO2. So yeah, CO2 from the absorption enhanced steam reforming gas mixture. That's the type. I think we have no much more time to talk about the details, but just wanted to show you another application of calcium looping, which is again going to be demonstrated at a megawatt scale. Finally, when talking again, we mentioned economic, evaluations, etc. The main thing when comparing CCS, calcium looping, or any other technologies that's supposed to be, deployed or commercialized, we always can see, I don't know why it's happening. I really have no explanation. We are comparing technologies based on levelized cost of energy or levelized cost of CO2 avoidance or something like that. But we really need, to be comparing technologies based on their value. For example, what's value of variable electrical output? Okay, it could be very cheap. There is no dispute. But what's value of that when compared with power generated in, for example, natural gas-fired power plant with carbon capture and storage? That you generate that electricity and changing load, changing output when you need. In that case, in the former case, you don't need even. Okay, just to be clear, in the case of variable output, you need something such as energy storage, or to balance that by flexible generation. To balance that by flexible generation, we use fossil fuels such as natural gas, and that's another reason, even in the case of high penetration renewables, we still need CCS and technologies such as calcium looping to balance energy grids. These are some ideas of some our published papers. You will have probably these slides. So I will not be paying much, will not now talking about that. It's already published. Wanted to show you that we need to look about synergy of our CCS calcium capture processes with other processes. In this case, in this paper, we demonstrated that the calcium looping system that we use for carbon capture can operate as energy storage, thermochemical energy storage system. And we have 3 points where how we can store energy. We have a silos for sorbent, limestone. So we can run reaction like reaction of carbonation of lime, which is a geothermal process with high demand. If we have high demand for energy, for electricity, we can be doing hydration of this sorbent, which is also exothermic process. Or we were talking about some difficulty for this process, not difficulty, increasing the cost of the process if you have cryogenic oxygen separation. But why we don't use oxygen tank and we run oxygen generation only during the time when we have surplus of electricity, cheap electricity in the system. That's one example. Another example is just after that we focused also on the oxy-fuel combustion as component, which is anyway component of calcium looping. But the principle is that we very economically can run carbon capture processes based on calcium looping in the case if we integrate them properly in energy system and use them also at the same time for energy storage in that case, even we can generate some additional income, not costs. And to be saying only carbon capture and storage is expensive, carbon capture processes are expensive. So I wanted to know, just to remind you my first slide, it's not necessarily true that carbon capture processes are expensive or not economic. This is another opportunity, again published, where we demonstrated, but with realistic, not optimistic assumptions, that we can decarbonize iron and steel industry at the cost for CO2 avoided, order of magnitude 15 euros, dollars, whatever, per ton of CO2 avoided, which is already commercially viable, economically viable now. We proposed exploiting synergy between processes, because in a lime production process, you already have a lime kiln, which is calciner, and you need lime in blast furnace. If you just add one more reactor here, one more vessel, which is carbonator, you reduce in that case capital costs of the technology, and you decarbonize whole process, and you have from that process, from a calcium looping process, you have feedstock for blast furnace, lime for blast furnace. So there is no waste from this process. And economic analysis is showing that really could be cheap, not expensive. And about carbon negative technologies, it's not, we'll not be talking now much, because especially Mei Hong already mentioned them, but we had some ideas. If we produce by a kind of calcium looping system with carbon capture, cheap lime, not in lime which is not expensive, but also we call that carbon negative or carbon neutral lime. That carbon neutral or carbon negative lime from this process can be used to decarbonize many other industries, just as using that material. So I think I finished, and I don't know, whether is there any time for question, and I'm very happy to discuss or for any question.
Thanks, Professor Manovic. That was excellent talk, and a lot of information about calcium looping solid. It's mainly high temperature solid based carbon capture.
Mine may be high temperature, but just now, due to time constraints, I didn't talk. We can use even for direct air capture, and it will stay on these slides. Direct air capture. Once you produce lime, you can expose lime to be capturing CO2 from air, and that's already being commercialized. Yeah, at room temperature.
Yes. We are also working in that area. Yes. So probably I have one question. You mentioned that the produced CO2 is corrosive. Can you elaborate that a little bit more?
CO2 from calcium looping process is corrosive because you have calciner, which you are where you have oxy-fuel combustion. So in that you have oxygen definitely. That's one thing. Another thing is if you are using fossil fuel, which in most cases, you have steam. You are generating steam, so you have oxygen, steam, and some sulfur dioxide will be in the system.
Okay.
So but
okay, it's from the oxy-fuel combustion it produces some and the CO2.
Yeah.
Okay.
But again,
so could that be externally heated instead of using oxy-fuel heating?
There we published one paper a few years ago about externally heating calciner to regenerate calcium carbonate. So that's basically still as a concept in that paper. But yes, there is possibility. That's a technical solution to externally heat, to consider heat transfer through the walls and to heat in that way calcium carbonate to calcine. Yeah, in that case, that would not be issue. Would not be produced corrosive gas.
Okay, I see. I understand now. Yeah, thanks. And yeah, that was very interesting. So I think we can finish here.